So in 21, we're talking about the form of our equation. So y equals a times b to the x. So this is the form that we've seen most of our equations set up in, our exponential equations. And we want to know, what does a represent in this equation? And what we talked about in problem 20 is that a is going to represent your initial value, or your y-intercept. Might be another way that we phrase that. And then b is going to represent our multiplier, or our growth. Or, because technically it could also be our decay, so how our equation is either getting bigger or smaller, depending on the situation. Then we want to know, how can you identify a by looking at a table? So when we're looking at our tables, we find a by looking at wherever our y-intercept is. So whatever part of our table is, the x value is 0. So how can we identify a? You can find a when the x value is 0. If we're talking about a particular situation, we can find a as the initial value. For example, in the number 20, we had the problem where they were talking about a company. So the founders represented our initial value, or the initial number of people working at the company. Now, when we're looking at our different representations for b, what we would want to be talking about is like the multiplier. So if we're looking at our tables, we can see that growth or decay by what do I need to do to get from one number to the next. So I think of it as how the pattern or data or numbers, whatever you want to call it, is growing. When we're looking at, for example, a graph here, it can be a little bit harder to see what's going on. So a lot of times I like to write our points that we have on a graph as a table to make it a little bit easier to see what we're looking for. Because then we can look back at our table and it's a lot easier to see, oh, I'm multiplying by 0.8, I'm multiplying by 0.8, over and over and over again. So this is something that applies really nicely outside of our high school classrooms, because exponential functions represent interest, which is something that you see in bank accounts, pretty much any sort of saving situation. So suppose you have $1,000 to invest in two investment options. You can invest in bonds, which pay 8% simple interest, or you can put your money into a credit union account, which pays 8% compound interest. Which option will you choose to make, or which option you choose will make a difference in the amount of money you earn? Examine these two situations below. So we're going to start with simple interest, which is going to be part A and B here. So I've recorded their table. And what we're looking for is, first of all, how does this grow? And in simple interest, we would think that it's going to be very similar to what we've been talking about, this exponential situation. However, when I look here, I see that I'm just adding 80 each time. I'm not actually multiplying by anything. So simple interest is adding the same amount each time. So in our fourth year, we would follow that same pattern. We're going to add 80, which would put us at $1,320. And that's where we would be with simple interest. So simple interest, we're just adding the same amount every time. And that number usually represents a percentage of the initial value. So $80 represents 8% of our initial value, our initial $1,000 that we put into the account. So we're just getting 8% of $1,000 added on every single time. Now, compound interest, which is what we're going to look at for parts C and D, is a little bit different. So we start with the same initial value, so we put our $1,000 in. And it says, instead, if you invest $1,000 in the credit union at 8% compound interest, which is compounded once a year, its value will grow as shown in the table at right. Why is there $1,166.40 in the account at the end of the second year? Explain how the compound interest is calculated. How is it growing? So I see the same first year. Both of them have $1,080. However, what they're pointing out is that here we see a difference. So how are they getting this number? Because it's not just adding 80 like it was for simple interest. So I'm going to look and see, is there some sort of pattern in multiplying instead? Because adding isn't going to work like it did up there. So if I do multiplying, to get from my first number to my second number, I multiply by 1.08, representing 108%. Now I'm going to test if that 108% works to get from my first year to my second year. So I'm going to take 1,080 and I'm going to multiply it by 1.08. 1,080 times 1.08. And I do get $1,166.40. So I am multiplying by 1.08. Just to test to be 100% sure this works, I'm going to take $1,166.40 and multiply it by 1.08, and I should get this number, which I do. So the way that compound interest works that's different than simple interest is you're gaining 8% of the total amount of the money in the account, the initial value, plus what the interest you already have in the account. So this is what you actually see in most bank accounts these days, is they give you interest of the total amount of money in the account, whether it was originally the amount you put in or interest that you've earned by leaving the money in the account. So our interest here, let's see. It's growing by taking 8% of the total value of the account, not just the initial. So that's how these are different, is in our original equation, our simple interest, we were getting 8% of only the initial value, so only of that original $1,000. 8% over and over and over again. Down here, we're getting 8% of the $1,000 to get here, but then we're getting 8% of the $1,000 plus the $80 of interest that we got. Then we're getting 8% added on of the original $1,000 and the $166.40 of interest we got over and over and over. So to get to year 4, we're going to take $1,259.71 and we're going to multiply by 8%, or 1.08, representing 108% of my original amount, which gets me to $1,360.49 with rounding, because it's 48.6, which we can't have 0.6 of a cent. So which type of account, a bond with simple interest like we had up here, or with compound interest like down here, grows more quickly? And hopefully what you're seeing is that over the same amount of time, so over 4 years, this account down here ends up with $40 more than this account up here. And the reason is because you're getting that interest on the interest you've already accrued. So we would want to say that compound interest grows more quickly than simple interest. Then we're going to move on to 31.